Hello students, welcome to this video and we are going to talk about second order equations of elliptic type. So as I told you, if you have a linear second order equation, let's say in 2 dimension, you can just look at the discriminant, which is b square minus 4ac. If that's going to be negative, you have a elliptic equation in your hands, right? And what is the prototype of it? So let's give you an example. First of all, start with an example. The first example is this example, the Laplace equation. Yes, if you remember Laplace equation. So see, there is two way of writing it. So essentially mathematicians generally write it like Laplace of u. Okay, so this is given by, and in 2 dimension I am just writing it. It is u x plus u y y, okay, equals to 0. Yes, but in most engineering text, right, or let's say if you are from engineering background, you may have seen it like gradient square. Yeah, now this as a mathematical symbol does not make any sense, okay, but you can think of it as a notation and we can just write it like delta. Okay, think of it as a notation. Clear? Okay, so we can you can also see people write it like del squared u, so like this. Yes, and that is called the Laplace also. So similar sort of thing. This is called the Laplace equation. Okay, Laplace equation. Now don't get confused with the equation which looks similar. So it will look like this, delta square. That's a fourth order equation. Yes, yes, fourth order equation. These actually models beam movement and all. So I mean, don't get confused between this inverted this pyramid delta and the inverted pyramid. Okay, so this is called delta. This is called a delta. Okay, capital delta essentially. Okay. So but throughout this thing I'm going to write like this delta only. I'm not going to write it like del this del square. Okay, just because I may get confused. Okay, so the other example, so this is called Laplace equation. If delta, so if this is called the Laplacian of u. Okay, so Laplacian of u equals to 0. This is what we call it. Okay, now see, let's say if I'm writing Laplacian of u equals to g. Okay, and let's say g is just a function of x, not a function of u. So that equation can also be treated, and that is called the Poisson equation. Sorry, this is called the Poisson equation. Okay, right. Now here you see the thing is g which you have, this x is in two dimension I'm doing, so in 2D, in 2 dimension. Doesn't have to be 2 dimension. Yes, I'm just doing it for 2 dimension just for us to understand. If it is 3 dimension, you just add one more. So essentially, let's say Laplacian of u in 3 dimension will look like this. Laplacian of u in 3 dimension. So basically u is a function of x, y and z, let's say. And you can guess what is it. It is u xx plus u yy plus, with respect to z, u z z. Clear? Okay, so in 4 dimension you can just do it, go on doing this thing. So here this x, this depends on the dimension. So in this case, since I am taking it to be 2 dimension, x is x1, x2. Okay, so maybe I can write it like this. It is g of xy, 2 dimension, because I am starting in xy, I am just writing it in xy. Okay, so this is called Poisson equation. Now there is another very important equation. This is called the Helmholtz equation, and the equation is Laplacian of u. So this is again very fundamental equation. I will tell you why. Minus Laplacian of u equals to lambda u. Okay, so this is I mean, generally we does not call, so the name of this equation is called the Helmholtz equation, but we actually call this equation as the eigenvalue problem. You remember, you see eigenvalue, if you remember, what does it look like? It look like this, right? U double prime plus lambda u equals to 0, this sort of equation, right? So you see in 1 dimension u double prime is nothing, in higher dimension it actually becomes u Laplacian of u, right? And this is plus lambda u equals to 0. See, this is, and this equation is exactly the same thing. So essentially this is nothing but the eigenvalue problem in higher dimensions. Yes, this is called the Helmholtz equation. Okay, and what is lambda? For now you can assume lambda to be positive constant. This is always, we are always assuming lambda to be positive constant. Okay, right. Now there is another equation which is very fundamental equation. Of course, this equation, there is a time dependent variable of it, the original equation, but I am just writing it the steady state. Steady state means basically after some times the system stabilizes and then it becomes independent of time. Yeah. So that equation, what is it? It is called the Schrodinger equation. You have probably heard it in your physics courses. So it is given by Laplacian of u plus lambda minus qx, okay, times u equals to 0. So this is called the Schrodinger equation, time dependent independent Schrodinger equation. So this is time independent, or if you can also call this the steady state. Whatever you want to prefer, you can write it. Steady state Schrodinger equation. Schrodinger equation, very important equation in terms of physics. Okay. So these are essentially some equations which are of elliptic type, and of course we want to study these equations. That's the general idea. Yes. Now see, I will start with one definition and then I will go with the more detailed version of it. So a definition which we are going to use it. So this is a small definition. So basically in this part you will see me talking about something called a harmonic function. So all of this equation, first of all, this is defined, we are always defining it in xy, which is in some domain D. Okay, this is a domain. What is a domain? Domain, as I have probably told you, it is an open and connected set. Connected means essentially you have a, so let's say this is your domain, right? So basically what I'm trying to say is this, if you take any 2 points x1 and x2, you have a continuous path, okay, which joins x1 and x2, and the path totally remains on the domain D. This is our definition which we are choosing. So basically it is an open set and it is a connected set. Okay, so I am taking my xy from there. Of course, as an example of a domain, you can think of the whole space R2. That's the domain. Yeah? So you can think of this whole problems for all xy in R2, and or you can also think of it as some, let's say, open unit ball. So as an example of a domain, let us look at some example of a domain. Maybe I can write it properly. Let's do this before I defining this. So first of all, I will define something called a domain. Okay, and I'm going to define domain in R2. Yes, see, there is nothing special about R2. You can exactly write down the same thing for Rn also, absolutely no issues. So what is here? An open and connected set, and connected set in R2 will be called domain in Rn. Okay, in R2, sorry. You can talk about Rn also, absolutely no issues. Okay, so what does that mean? Of course, you know what an open set is, right? So that is not a point. What we want to talk about is a connected set. Let's just understand the connected set. Connected sets are what? Connected sets, we will define it as for any 2 point x1 and x2, x1 and x2, okay, for any 2 point x1 and x2, what you have is there exists a continuous path joining x1 and x2, joining x1 and x2, and lies entirely on the domain itself. So basically on the set itself. Okay, so essentially what I'm saying is this is very intuitive, right? You take any 2 point, if it is connected means it's not like there are no gaps, no holes, nothing like this. So essentially what I am saying is this, you have 2 points, let's say, in 2 dimension. Let's say x1 is a point and x2 is a point. So basically these are tuples. It's just a point in 2 dimension. Now what happens is, you can actually, what I'm trying to say is, you can join those 2 points. Yes, there is a path, this is a continuous path which joins x1 and x2 such that the path lies in that whole set. That's a connected set. So let's say if my set is this and this, two union of this. Now you see, if I take one point here, one point here, there is no way I can have a connected curve, continuous curve which actually lies to in the set itself, and I mean joining those 2 points, right? That's not possible. So that's not a connected set. Okay, right. So basically open connected set is all we demand for this whole thing to work. Okay, so we are always going to assume that. Fine. Now we will define something called a harmonic function. Harmonic function. So what is an harmonic function? Essentially what you want to do is, harmonic functions are functions for which Laplacian of u equals to 0. So u in C2 of D, I will explain to you why, is said to be harmonic, So basically we will call it a harmonic function if Laplacian of u equals to 0. Okay, so I should write it properly. If Laplacian of u at the point xy equals to 0 for all points xy in D. You understand? For every point in that domain xy, in the domain D, what we want is Laplacian of u equals to 0. Okay, so let's look at some examples of it. Maybe I can do it in the next page. Yeah? So is it clear? So essentially we are looking for some solutions of the Laplace equation. Whatever the solution is of Laplace equation, is call it a we call it a harmonic function. Okay, so for as an example, you can think of it like this: u of xy equals to, let's say, constant 1, constant 1, 2, whatever, some constant. Yes. Okay, so and in what is our domain? Domain D, I am choosing it to be R2. Let's choose it. And you do realize, you see, uxx is going to be 0 and uyy, so with respect to y, this is also going to be 0. Hence uxx, that will imply that Laplacian of u, which is uxx plus uyy, this will be 0 for all xy in R2. See, it does not depends on xy, right? Okay, so this is always so any constant if you choose, that is always going to be a harmonic function. Okay, let's look at another example. Let's say that u of xy equals to ax plus b. Ax plus b, where a and b are constants essentially. A and b are constants. Okay, so if a and b are constants, see what happens to ux. Let's just calculate it. It becomes a, and uxx means the derivative of ux with respect to x, that is again going to be 0 because a is constant. And similarly uy, if you choose uy with respect to y, see there is no y component here, so essentially that is going to be 0. So what happens to this function? Is it harmonic? Of course it's harmonic. So therefore, and uyy will be 0. Okay, so if you combine those two, you have that Laplacian of u is going to be 0. Clear? So that's an example. Of course, you can, you can, change it to uxy. So similar sort of example I'm writing. Uxy equals to ax plus by, and you can see exactly similar sort of thing happens. See, if it is by, this becomes b, and but the second derivative becomes 0, and you are done, right? You can also change it to ax plus by plus c. Then also it becomes harmonic. Yes. So all of those variations are always possible. So keep that in mind. Yes. So essentially this is kind of linear, if you can think of it like. Okay. Now what are other examples of harmonic functions? Okay. See, let's say u of xy. So nice example. So these are very basic examples, right? X square minus y square. Let's just look at it in R2. Yeah, I am not talking about any domain in R2. If you want a domain, you can take it to be an unit circle. Absolutely no issues. Okay. Right. Now, what is ux? Ux is 2x and uxx is 2. Clear? And uyy. What is uyy? Uyy is minus 2. Yes. Therefore, uxx plus uyy is going to be 0. Yeah, so this is also an example of a harmonic function. Yes. Now you see, in this whole thing, I use this fact that u is in C2 of D. What does it mean? It means that all second order derivatives exist. So in 2 dimension, what are the derivatives? Uxx, uyy, uxy and uyx, and these two are basically same, right? Mixed derivative equality. So essentially all these derivatives exists and it is continuous, exist and is continuous. That's what it is saying, then it's continuous. I hope this is clear. Then we say that u is in C2. Okay, so then we have something called a harmonic function, and if Laplace u equals to 0, and then these are the examples of it. Of course, you can create many more examples, absolutely no issues, you can find it. Yeah. Okay, we will talk about harmonic functions much more, yes, but for now what I am going to do is I will set up the problem first. Yes, so what are the, see, let's say in one dimension, yeah, what happens? One dimension in ODE theory, you have this equation y double prime plus, let's say, y equals to 0. Yeah, that's an equation. Now I want to study this equation. What do? I generally look at well-posedness of this problem. Well-posedness, we talked about it in the beginning of the course, if you remember. Well-posedness, what does it say? It says that whether the equation has a solution or not, whether the solution is unique or not, it depends on the boundary data or not. So here a very important thing is boundary data, you see. The point is this: existence is fine, but the thing is uniqueness. For a uniqueness to work, you need some data on it. So let's say this equation has infinitely many solutions, right? So without a data, finding a unique solution is going to be a issue. So what happens is, and of course well-posedness also doesn't make sense, because the thing is, the third point of well-posedness actually talks about what is the dependence on data. So basically if the data changes, the solution also changes a little bit. Yeah. Okay, so what do we want? You see, what we want is this: we want some boundary we want some condition here. So there are two conditions in ODE which you have already learned. So let's say this is defined in closed AB, interval AB. So you have this condition, right? Let's say y at the point A equals to some alpha, and y prime at the point A equals to beta. This kind of problems are called initial value problems. Okay, and what happens is, generally there is another boundary condition which you can talk out. So let's say you are given, so here you see why it is called initial value, because you are given data only at the initial point A. Now, so you see in higher dimension what happens is, so you see this is boundary data at a point A. You can choose another point also, absolutely no issue. So basically it depends on one point, yeah, and then you can do it. In higher dimension this does not really work here. So what we need to do is, essentially here we need to know what happens on the boundary. Yeah, so you see here also you can think of it like this. Let's say there is another data which is like y at the point alpha is, let's say, A equals to alpha, and y at the point B equals to beta. So basically there you are saying that B equals to beta. So there you are saying that you know that what y does here and y does here, and I want to find y. Yeah, this is called a boundary value problem. Yeah. So initial, you remember the eigenvalue problem which we did, those are all boundary value problems if you just look at it. Initial value problem is you are given some data at some point, initial point, here also, any point it is given, and you have to find out the solution. That's different. So in PDE theory, what we do is we basically study the boundary value problem, because the idea here is we have to know, so let's say we know some data is given on the boundary and we want to find the solution. So let me give you an example what I'm trying to say. So the first boundary value, so what are the boundaries? So there are like different type of boundary values which you can talk about. So the first boundary value, so that we call, so boundary values, boundary values. You understand? So see, boundary value problem. Okay, let me give you an example and then I will explain to you what I mean by this. So first boundary value is called the Dirichlet problem. Dirichlet problem. Okay, so what is Dirichlet problem? Let me explain. Basically, if I am saying that we are talking about a harmonic function, yes, so let's say I want, this equation is given to you, Laplace u equals to 0. Yeah? See, doesn't have to be this equation. You can have any other equation like this. Absolutely no issues. Or A, B, C, D, any of them. Absolutely no issues. I'm just talking about this equation in the context of this equation. Basically, this equation along with some boundary condition, right? Okay. So let's say that, so our equation here in hand is Laplacian u equals to 0. Okay. And now I want to put some boundary values. Okay, so I am saying that on the boundary u does this. So essentially this equation is, you see, in D is what? It is open, connected. So think of it like this. Let's say that the equation that gives information inside the domain. So basically I am saying that inside the domain u solves this part, and boundary value is what happens on the boundary. You see what happens on the boundary. You understand? Okay. So boundary value is, we are saying that let's say u does this. So let's say u equals to 0 on the boundary, u equals to something on the boundary, or the derivative of u is something on the boundary, and inside u solves this equation. Then can you find a solution? So that's the idea. That's the idea of the boundary values. I hope this is clear. Okay, let's look at it. See, Dirichlet problem. So essentially the problem is this. So Dirichlet boundary value. Boundary value. So I will write it like BV, because I have to write boundary values a lot of time. Okay. So essentially this is this. U equals to some f of s. Okay. Where f of s is a prescribed, already provided to you, that is given continuous function. On the boundary okay, B of the domain D. Okay, so see, you will be given the equation. That equation is defined in some domain, right? So of course, see, these things without the equation does not make sense. So we are actually assuming that we have this equation, Laplace u equals to 0 in some domain D. Clear? And then with this equation I am putting this initial condition. So given this domain, there is a boundary of the domain. On that boundary I am putting some continuous function. I am saying that u is equals to that continuous function on the boundary. Okay, right. Now you see, how do you interpret? So basically how does it look in real life? So as an example, how does it look? So let's say I want to solve this equation, Laplacian u equals to 0, on the boundary. This is in in the domain D, and here on the boundary of the domain delta D. This is called the boundary. So basically, let's say if I am writing D is the domain in R2. It can be Rn also, yes, R2. I will write delta D to be the boundary of a domain, boundary of such domain, boundary of the domain. I hope you know what are the boundaries, right? So let's say if you have a open this thing ball, then the boundary is essentially so basically let's say this is your domain, right? This is your domain. So open unit ball. The boundary is mod x equals to 1 in this case. Clear? Okay. So that's your equation. This is the equation which we need. I mean, maybe you are asked to solve this sort of equation, or you can change it to, let's say, 0. You can change it to 5 or 1, some constant. That is continuous function. Yes. Okay. So let's for now let's just write it to be 0. It looks good. Or you can change it to some continuous function also. Absolutely no issues. Okay. Right. So what does it physically mean? Just get an idea of it. So physical interpretation. Physically. Okay, see the solution of this problem. So basically this is called a Dirichlet problem. Not with 0. I mean, you can change 0 to any f and still it's called. So basically this problem, Laplacian u equals to 0, the Laplace equation along with boundary value problem. So essentially what I'm saying is this Laplace equation plus the Dirichlet boundary values. So this is called the Dirichlet problem. Of course, doesn't have to be Laplace equation. It can be some other equation also. So it can be Laplacian u plus c of x equals to u. It can be this sort of equation also. Absolutely no issues. This also with this Dirichlet boundary value, we will call it a Dirichlet problem. Clear? Is basically Dirichlet problem is some equation is given and it satisfies the Dirichlet boundary condition on the boundary. Dirichlet problem. Clear? Okay. So physically, what does it mean? It means the solution u of the Dirichlet problem. Dirichlet problem. So please understand, this is one example of a Dirichlet problem. You have to change it to some function f for this to be a general Dirichlet problem, and f is continuous. Yeah. Okay. So a solution u of a Dirichlet problem. Okay. As a steady state temperature distribution. Okay, in a body containing no source or sink. I will explain to you what I mean. Source or sink. Okay, with the temperature prescribed at all points of the boundary. I will explain later in our next video where are we getting this. What does it model? So basically, let's say Laplace U. Yeah, what does it model? Prescribed at all points on the boundary. For now, let's just fix the theoretical part of it. See, essentially what it is saying is this. Let's say you have a room, right? Some room is there. Yes, generally our room looks like a rectangle kind of thing. So let's just say that you have a room. Now the thing is this. Let's say you are putting on some AC, right? There is a AC here. You are putting on this AC and cool air is blowing here. So what happens is, you do realize when you start, the points near the AC gets cooler faster, and as opposed to the points which is away from AC. Now if you look at these dynamics in a long run, so let's say if you are running the AC for, let's say, 6 hours, 7 hours, right? So think of it like if you are running the AC overnight. What happens is, after some time, after 7 hours or 8 hours, depending on various issues, the temperature of the room stabilizes means it becomes steady. So basically a temperature here and the temperature here are basically same, right? Okay, so and what happens is, then it is not a function of time itself. So basically after some time, let's say t equals to, let's say, 5 hours, after t equals to 5 hours, the temperature here is 30 degrees and let's say here is 30 degrees. It becomes stabilizes, the temperature becomes steady. And then if you keep on running the AC and let's say the temperature is same, so basically you are running the AC on 25 degrees. I'm not changing the temperature. Yeah, so there is no, and I am assuming that this wall is such a way that it is properly insulated, so there is nothing coming in or going out. Clear? So there is no heat which is coming in or going out. Now after some time, if you stop the AC, what happens? If there is no heat coming in or going out, so it reaches this whole room reaches a steady state. So 5 hours or 5.30 hours, what happens is, essentially we want to yes, so we want to find out the dynamics. So let's say after some time, yeah, after it reaches the steady state, what is the diffusion? Yeah, if nothing comes in and goes out, so let's say that this boundary, in this case, what is the boundary? Boundary is this, right? Boundary is this. So you see, in this since there is nothing coming in or no heat which is going out, so basically it says that on the boundary, yeah, the u is basically 0. Yeah, there is nothing, there is no heat which is coming in or going out. That is why u is equals to 0. Let's say you can say that it is there is some part of it which is comes in and goes out, so you can model it using some function f which is continuous, and then u equals to f on the boundary. So essentially inside, what is happening? How is the diffusion model? Diffusion means how are the air particles getting cooled. So essentially the diffusion is modeled using that Laplacian. There will be other terms of it. I will talk about all of these here properly. But the thing is, the idea is this, that from, let's say, u equals to 0 on the boundary, if I'm saying this. So that's a boundary data, right? It basically says that there is no heat which is coming into the room or it is going outside the room. Okay, right. So that's the idea of Dirichlet boundary. Okay, so there is another boundary. Let's look at the another boundary. The another boundary is called the Neumann boundary. And again, this is very, very important. The Neumann boundary. Okay, and this Neumann boundary is the second such boundary which we can talk about. So what is the Neumann boundary? So let's say again Laplace u equals to 0 given. Yes, so I am assuming that Laplacian u equals to 0 in some domain D, which is subset of R2. You can think of it in R2, R3, R4, doesn't really matter. Now the boundary data, the boundary data or boundary values, whatever you want to call it, absolutely no issues, is basically del u by del eta equals to f of s on the boundary. Clear? So basically what it is saying is, initially for the Dirichlet problem, we are just saying that u equals to some function, u equals to, let's say, 0. Now what we are saying is u is not equals to 0, but the derivative of u in a certain direction. So let's say if you are talking about a domain which is a circle, right? Sorry, disk, disk, unit disk. Now at any point, let's say this is your eta, eta, and the thing is what I am saying is this boundary, because the thing is del u del eta equals to f of s on the boundary. So essentially you take any point, let's say x naught on the boundary, and you look at the direction eta. What we are saying is this, the the derivative of u, how u moves, how u changes in that direction, is given by f of s. Clear? So with integral f of s ds, okay, over del d is 0. Yes, so this is the so if this Neumann boundary is given, this is the condition we also need along with that. Again, I will again explain to you why we need this condition here, but anyway, we need this condition, right? So what is delta del u by del eta? Del u by del eta is the directional derivative, once again, directional derivative of u in the direction eta, okay. So it is essentially the directional derivative, yeah. And what happens is this, of course, on the boundary. So any point on the boundary, you look at the derivative, and in that derivative we are just basically looking at what is the change in u in that direction, okay. And this condition is called the compatibility condition, yeah. We are not in a position right now to explain to you why we need this compatibility condition. Basically it comes from something called a integration by parts, right? Yeah, I will explain to you later, but for now, since we are just talking about boundaries, we are not going to talk about Neumann, this compatibility condition right now, okay. But the thing is, this condition is required. Without this condition it won't work, okay, right? Now see here the solution u. So basically, let's say this equation is given and this is your boundary condition, So physically the solution u, how do you interpret it? Solution u, okay, may be interpreted as a steady state. As a steady state means, see, this heat diffusion problem, let's say that problem has this form ut minus Laplacian u. It looks like a heat equation, right? Laplace is this form. You see, if the system becomes steady, what happens? The time becomes, in this case, so the u becomes independent of time. As I told you, after some times it stabilizes, right? It does not change with time. So essentially ut, in this case, what is the change in u with respect to t? It will be 0, right? And then it only left out with your Laplace u. So essentially here the solution u may be interpreted as a steady state heat distribution okay, in a body containing no heat sources, or heat sinks, okay. Sinks means basically something, there is a hole where, or think of it like this. So essentially it drains down, yeah. So there is no source. Source means it adds up, right? The heat adds up. There is no something. There is nothing which actually adds the heat up, or there is no sink. So it actually the domain from the domain the heat releases. There is no such condition. Huh? So we are saying that this actually represents what the solution U represents the steady state heat distribution, how the heat is distributed in a body which does not contain any heat sources or heat sinks. Okay, when the heat flux across the boundary is prescribed, okay. So basically heat flux means the change in how much it is changing essentially. Yes. So across the boundary, what is the how much the there is an exchange of heat near the boundary. So basically flow of the heat. So that is actually given by del U del eta. Okay. And what about the the compatibility condition? The compatibility condition actually says that the net heat flux across the boundary should be 0. The compatibility condition implies, see, this is integral over the boundary is 0, right? What is integral? Integral is basically sum, right? So the compatibility condition says that the net influx, heat flux across the boundary is 0. Clear? Okay, so this is Neumann boundary condition. We have two more. So another one is called the this is the fourth boundary condition. Okay, this is called Robin boundary condition. Maybe I can do the mixed. Let me do the mixed boundary condition first. Mixed boundary condition. Okay. So what is mixed boundary condition? Mixed boundary condition is essentially, again, you have this equation Laplace U equals to 0 in some domain D, okay, which is subset of R2. It can be Rn, and also the function satisfies del U by del eta plus h of s. H is a continuous function. I am going to write continuous function times U equals to f of s. This is on the boundary del D. Clear? So where h and f are continuous functions. In some domain. So I am not putting all these domains here, otherwise it will be complicated, but basically they are continuous functions. So for example, you can think of it like this. So say del U del eta plus U equals to, let's say, 0. Yeah, that's an example. And so essentially you will be given, let's say, Laplace U equals to 0 and this condition is given. Can you find an example? Can you find a U which solves this equation? Of course, you do realize U equals to 0 of course solves this equation. You see, U equals to 0 solves this equation. Clear? Okay. Right. Now, what do I do? Yeah, this thing, physical interpretation, right? So you see here, U may be interpreted okay as a steady state, steady state means after sometimes it is independent of time. So the whole state of the the system becomes steady, right? It does not depend on time anymore. Steady state temperature distribution, okay, in a body. So you see, since Laplace U equals to 0, it basically says that is the steady state temperature distribution in the body. Now the point is this: the boundary data will determine what exactly I are trying to do. Del U del eta plus h of s U equals to f of s means that the in the body, and from the boundary okay, boundary of which the heat radiates freely, okay, into the surrounding medium, of prescribed temperature. So you see, this actually says if you take F to be 0, H to be 0, 1. So essentially it says del U del eta plus U equals to 0. Yes, and if you think about it, it is basically saying del U del eta equals to minus U, right? So what does that mean? It means that the flow of U across the boundary in the direction eta is basically proportional to U itself. Is it okay? Negatively proportional, but I mean, you get the point, right? Okay, so that's what. So basically it says that the heat radiates. Radiates means goes out or comes in, it depends, but essentially it radiates freely into the surrounding medium. So whatever the surrounding medium is, it gets radiated there. Yes? Okay. So that's mixed boundary. So this is 3. And there is another boundary condition. It's called a Robin boundary condition. It's called a Robin boundary condition. So this is the last one. Robin boundary condition. So anyways, again, same thing. Yeah, we are actually looking for Laplace U equals to 0. So our equation is given Laplace U equals to 0, let's say, in some domain D, which is subset of R2. Yeah. Okay. And the boundary condition which we have is essentially what happens is the boundary in this case, let's say there are 2 different boundaries. So yes, and let's say this is your boundary B. Clear? And sorry, this is your boundary del D. Okay, and what happens is this, and let's say from here to here, yeah, this is B1, the first boundary, and this is B2. This part to this part, this is B1. This part to this part, this is B2. Yeah. So here, what we are doing is we are prescribing, let's say, U equals to F1 of S. So essentially, Dirichlet here and Neumann here and Neumann here. So del U del eta equals to F2 of S. Is it okay? Yeah. So this is basically, I mean, we are using both Dirichlet and the Neumann, but in different parts of the boundary. Okay. So here what we do is essentially the boundary condition looks like this: F1 of S on some part of the boundary B1 and del U del eta equals to F2 of S on B2, where B1 plus B2 is going, sorry, not plus, it is a sets, B1 union B2 is going to be del D. Is this okay? And these sort of things are called the interior boundary condition. There is something called the exterior boundary condition, but that is not in your syllabus, so don't worry about it. These are called interior boundary conditions. If you understand this, this will be more than enough for you. Okay, so essentially what am I doing is this: I'm changing this part into 2, and I'm saying that in some part of the boundary U satisfies U equals to F1. So here where F1 and F2 are continuous. Clear? So I'm saying some part U is equals to F1 and in some part the Neumann boundary condition is satisfied. Now you have to find a solution of this problem. Yeah. So these are much more complicated problems than the just Neumann or just Dirichlet problem. You understand that, right? So these are, so essentially you will be given the equations and you will be given this boundary condition, and the question will be that whether you can find a solution of this problem. And this is the point. This is how I will start from here, and then I will show you how to work out problems, so how to handle problems like this, and we'll start only with the elliptic part. Okay, so with this I'm going to end this video. Thank you.